this is A. Somaiah, working as assistant professor in the Department of Mechanical Engineering at Institute of Aeronautical Engineering, Hyderabad. So today I am going to discuss the stress strain diagram for various materials. So this is for third sem mechanical engineering as part of solid mechanics. So the purpose of drawing the stress strain diagram for any material is to determine its mechanical properties, its various mechanical properties, like to find out modulus of elasticity and yield stress, ultimate stress, fracture stress, toughness, strain hardening. All these properties can be revealed once you draw the stress strain diagram for any material. So why these properties are required? Because the properties are required in order to apply a material into a service. Suppose I need a particular material that is going to be applied in a machine, where we need to know what is the maximum load it can bear. So in the machine, what is the based on that, the material can be decided whether it is fit for that particular machine or not. Similarly, what is the elastic limit where it will fail? If we know the ultimate strength of material, then we will decide the factor of safety of that material. Based on that, the design will go on. So in modern design offices, a special care is taken at the time of designing a structure that it should be able to withstand the stresses under the various conditions without failure. This in order to avoid the failure of a material during the surveys. So we should know various values of a material. So for doing so, it is very essential to have a complete information about the various properties of the selected material and its dimensions. This information can be obtained by experimental investigations in a well-equipped material testing laboratory. Basically, the materials are classified into 4 groups. So they are elastic materials, plastic materials, ductile materials, and brittle materials. So in engineering purpose, based on the requirement, we will select which type of material is going to be required in particular purpose. So various materials which are going to be used in a engineering purpose are classified into 4 categories. So here the classification of materials. So in general applications are divided into 4 groups. One is elastic material, another one is plastic material, then ductile material, finally brittle materials. So the purpose of different materials will be used in different purposes. According to the requirement, we will choose the type of material and we will disclose its various properties, mechanical properties, and we will try to apply into the particular application. Elastic material. What do you mean by elastic material? So in a universal testing machine, so if you apply the external loading on a material, so after removing external material, the body is get back to its original position without any damage. So that type of material is known as elastic material. For example, spring or rubber, etc. If you take the spring and try to pull on either side, and after removing external loading, then it will come back to its original state. Still, if you go on applying load, then it will not come back to its original position or original properties can't be obtained by the spring. That is plastic zone. But after external load is removed, if it is coming back to its original state, such type of material is known as elastic material. Similarly, plastic material means once the external load is increased beyond the elastic limit, then it enters the plastic zone, where if you remove the external load also, it can't come into its original position, or it can't acquire its original properties like shape, size, dimensions, all that will be lost. So permanent deformation will be taking place. The permanent deformation of a material is known as plastic zone or plastic material. Then ductile material. The ductile material, it will undergo a deformation, a long deformation. Considerable deformation can be obtained in case of ductile materials without failure. So, but in case of brittle material, if you apply external load, what happens? It gives a little deformation. Then suddenly the breakage will take place. So such type of material or glass, ceramics, cast iron, etc. These comes under a brittle material, but ductile material examples are brass, bronze, steel, lead, etc. Aluminium. All this comes under ductile material. It gives a considerable, noticeable deformation if you apply external load after the elastic limit. You can see its deformation. So such type of materials are ductile materials. So the stress strain diagram, before going to draw a stress strain diagram, otherwise the relationship between the load and deformation of a material, the load and deformation relationship of any material is going to be drawn. Otherwise the stress versus strain, the sigma versus epsilon, before going to draw the stress versus strain curve, we should know where it is going to be drawn, where it can be obtained, what are the various values to draw such type of diagram. So for that purpose, so here we are going to discuss the universal testing machine, UTM. So this is also known as universal tester. The purpose of universal testing machine is why it is called as universal testing machine, because it is used for a multi number of purposes. It can be suitable for tensile testing, compression testing, bending testing, shearing testing, etc. So multiple types of the tests or experiments can be conducted on this machine. Therefore, it is known as universal testing machine. So here our stress strain, our diagram, stress strain diagram for different materials. So for whatever the material it is, that material is going to be tested on this machine only. That's why we are going to discuss about this machine. So basically it is having two units. One is a loading unit. This is known as a loading unit, and this is known as control unit. It will have these two units. The purpose of loading unit is the exertion of the load held in the loading unit. So we have to apply the load gradually by inserting a specimen into the mechanical grips. So that is the purpose of a loading unit. And a control unit is, the purpose of control unit is the test results and loading, the way of loading, etc. can be obtained or can be controlled from this control unit. These two are the major units in our universal testing machine. So after applying, after taking a suitable specimen, and we will fix it into the loading unit. So in that loading unit, there are three crossheads: middle crosshead, upper crosshead, and lower crosshead. We will keep the tensile specimen in upper and middle crosshead. So here we will in the mechanical grips we will fix our tensile specimen. Then we will apply a gradual load. So then there will be a deformation, and we are going to apply. We are going to note the various load values and deformation values, etc. Deformation values can be obtained by extensor meter, but the load values can be drawn from this dynamometer. Here dynamometer is there. So from this we are going to obtain the various load values. So in the load unit, again there are three important parameters, three important devices. One is the load frame, upper, middle, and lower crossheads, and elongation scale. So this is a load frame. Here, in the load frame there are three crossheads: upper crosshead, middle crosshead, and lower crosshead. These two are fixed. So upper crosshead is fixed, and lower crosshead is also fixed. So the middle crosshead, this is movable. We can move, movable crosshead. So these three are the crossheads to conduct the number of experiments on this machine. And the elongation scale, the purpose of elongation scale is to measure the relative distance between the crossheads. The relative distance between upper crosshead to middle crosshead, or the relative distance between middle crosshead to lower crosshead, etc. These distances can be measured by using a elongation scale that can be fixed onto a loading unit. So in the control unit, so in control unit again there are three different parameters, different useful major devices are there. One is hydraulic power unit. So the hydraulic power unit purpose is here oil pump will be there in a control unit. There will be oil pump inside. So the purpose of oil pump is to provide non-pulsating oil flow into the main cylinder of the loading unit. So this flow helps in the smooth application of load on the specimen. Otherwise, if there is no non-pulsating flow, what happens? The sudden load will be applied or improper loading will be applied instead of gradual loading. Then the proper results can't be, proper mechanical parameters can't be revealed. That is the purpose of providing non-pulsating oil flow into the main cylinder, which is provided in loading unit. See, another device in a control unit. In a control unit, another device is load measuring unit. So this is a load measuring unit. So this can be varied within in the ranges of 0 to 100 kilonewtons or 0 to 250 kilonewton, 0 to 500 kilonewton. Similarly, 0 to 1000 kilonewton based on the material which we are going to apply the load. So based on its capacity, we are going to. So if the material, if we have taken the stronger material, if you use 0 to 100 kilonewton, so we can't obtain its proper results. So the material capacity should be within these limits. So then only we will get its the maximum. Otherwise, we can identify its ultimate stress. So that's why any material it has to fall based on that material. We have to choose the scale. So another device in the control unit is there are some control devices like electric and hydraulic control devices are there. The purpose of electric devices are to regulate the power, switch on, switch off, etc. So that type of functions can be done by using a electric control. And the purpose of hydraulic control, there are two valves, left one and right one. There are two valves are there. So the right valve, with the right valve, we can apply the load. So the hydraulic load can be applied by using the right valve, and the load can be released. The load can be released by using a left valve. So these are the purposes of the control devices. So we are now, after discussing about a machine which we are going to use for a tensile testing, where we will find out its testing diagram. So after the description of the machine, so then we will go for find out the specimen, various specimen cross sections, how to make the specimen, and what are the requirements of the specimen according to the ASTM standard. So whenever some external system of forces acts on a body, it undergoes a deformation. If a body is stressed within its elastic limit, the deformation entirely disappears as soon as the forces are removed. It has been also found that behind the elastic limit, the deformation doesn't disappear. So such type of zone is known as plastic zone. Some residual deformation will be left. So the tensile test specimen will be made in this form, dog bone shape. So these two ends, the left end and the right end, will be with a greater material in order to fix it into the mechanical grips. So after fixing into mechanical grips, it is not supposed to be come out of that grip, and also the material should not fail at this point. The material should not fail here or in this section material. So in order to ensure that the material should not fail in the grips, so the material in between these two grips reduced to the required diameter. Its diameter is greater than to the diameter in between AB. So this reduced diameter is gauge length. Within this gauge length only material will break down. So this is a narrow. Here we are making a curvature or filleting. So with some radius. So in order to avoid the stress concentration, because if it is made perpendicularly like this, the material will break down at this point only. So that's why in order to avoid such type of breakages of material, failure of material at the corners itself. It is to be provided with some fillet. So gradually the material is going to be decreased to the required diameter. It is 12 mm diameter. So in order to achieve 12 mm diameter from 20 mm diameter, so gradually we are decreasing the material from 20 to 12, so that the stress concentration factor will be uniform. So otherwise, various stress concentration factors like this uniformly distributed. So otherwise, the material will break down if you make a material with perpendicular like this. A sharp corner should be avoided in order to avoid the breakage at the corners or in the grips. So then the material will break down within the gauge length only. That is the purpose of providing a material. So we will consider the gauge length only for the calculation. So between AB, this is a gauge length. In between this only the material has to break down. So the material which is going to be tested in a universal testing machine will be prepared like this. And here different cross sections we can observe. So this is a circular cross section. If it is a circular cross section, it is to be made like this, and this is a rectangular cross section. So a rectangular sheet that can be made like this. Next, take a specimen of mild steel. So, and it is to be made according to the STM standard. So in this manner, and if we plot the stresses along the vertical axis, a stress we will consider. So before going to stress strain diagram, so the stress or load will be taken on y-axis, or it can be denoted by sigma, and the strain is taken on y-axis, x-axis, that is denoted by epsilon. Okay, so now the relation after applying the load, we will find out the different loads at different stages, and we will identify over here, and at different points or during the period of testing. Then we will connect all those points to a smooth curve. Then we will get a stress strain diagram. So during testing, the purpose of providing this device, this is known as Extensor Meter. So Extensor Meter, the purpose of providing this Extensor Meter is to determine, otherwise to note down the deformation values. Deformation should be noted down during the testing. Once the load is applied, so gradually the material begins to elongate like this. So during elongation, so we have to measure how much of elongation is going to be taking place, and every time for that particular amount of elongation, what is the stress applied. These two relationships we will note down. So within the elastic limit, we will find out the load values, also elongation values, so that we can calculate the Young's modulus. So otherwise, Young's modulus can't be calculated within the plastic zone. So in order to determine, according to the Hooke's law, stress is directly proportional to strain within the elastic limit. That's why within the elastic limit, before the failure occurs, otherwise before material getting into a plastic zone, we will find out, we will note down different elongation values and different load values. So after that, we will put it into a stress strain that graph. There we will find out, we can achieve this diagram, proper diagram, how it is going to be happen. So once this extension meter is removed after reaching to the elastic limit, then material starts deforming, otherwise necking will be taking place at the ultimate stress. After that, the failure will take place. The type of load we are going to apply is a axis-centric loading and not transverse loading. We are not going to apply a transverse loading like this. So we have to apply the axis-centric loading, and original length is L. So after deformation, then it becomes L plus delta. And if you consider a transverse cut, you can find out the true stress. Stress is load upon area, and nominal stress or engineering stress is force, normal force by area. Original area at the time of the stress applied. So after applying some load, then there will be elongation, then reduction in a cross-sectional area, that area is to be considered, then we will get engineering stress. Similarly, true strain and normal strain also, change in length by original length, and the strain at the time of elongation. So this is a stress strain diagram. Once we fix this specimen into a universal testing machine after applying the gradual loading, then load has been applied at various stages, and we are going to be note down the various load values from the dynamometer at various points. At the same time, we are going to find out the elongations from the extensor meter at various points. So after noting down, if you keep all those values on a x and y axis, then we will get a stress versus strain diagram. So from 0 to A is known as a proportional limit. This A is known as proportional limit. Then elastic limit. B is known as elastic limit. So then yield stress, upper yield point is C, lower yield point is point D, and ultimate stress can be obtained at E. Fracture can be taking place at F. So if you attach a system to the universal testing machine, and with the help of a software, automatically this stress strain diagram can be generated with that software. So if there is no software, we can keep, there is a provision to provide a drawing instruments to the machine where it can generate the stress strain diagram. This is another method. If that manual method is also not available, then with the help of the values from the dynamometer, values from the extensor meter. So if you put into the graph about x and y, then we will get this curve. So in different methods we can draw this one. So but this is a true stress strain diagram we can see here. So but this is ideal. In ideal case, a mild steel can be elongated like this. So now at the proportional limit at point A, if you remove the external loading, so initially specimen at O, after applying the external load, it will be elongated. So like this, and the stress is this much. Okay, yeah, stress versus strain, this is a proportional limit. At that point, if you remove the external load, what happens? It can come back, and where you can draw a slope. The slope gives the Young's modulus of that material. So within this elastic limit only, but we can't get the elasticity in the plastic zone. So at the proportional limit or at the proportional limit, if you remove the external load without losing properties or without the residual strains in a material, the material can get back to its original state. So that is proportional limit, and at the elastic limit also it can get back, but some of the residual strains, the permanent strains will be remained at the elastic limit, but it can get back to its original position. So, but at elastic limit, ultimate yield point, at yield point, upper yield point, or at a lower yield point, if you remove the external load, it will not get back. That's why yielding is nothing but it's a beginning of plastic deformation of a material. So yield means the plastic deformation of a material. So after upper yielding, without applying a external load, the curve is coming down. So after that, what happens? So the strain hardening will take place. So due to that, the material will get hardened, and it requires more energy than point A, B, C, D, etc. So it acquires more energy in order to avoid the external deformation. So it will not allow to failure that much of easily. So during this, we can find out the ductile properties. So how much of elongation is there? This indicates the ductility of that material. So after that, even though still we are going to increase the load, so this is also resist the deformation, resist the external load, and there we will get the ultimate stress. After that, at ultimate stress, necking of a specimen will take place. So gradually the area of cross section will be decreased at the ultimate stress. So without applying the much load at the elastic limit, it will come down and failure will take place at point F. So these are the various zones we can observe here: the elastic zone, plastic zone, and the strain hardening. Now the area under the stress strain diagram, area under this curve is known as area under this curve is known as the toughness. This gives the toughness of a material. The toughness of material is nothing but the ability of a material to absorb the energy before fracture. So therefore it gives the energy or the capacity of a material before it fractures, how much of energy it has got. So energy measured in joules for unit value. So in joule for mmq we will measure the energy absorbed by the specific material. So that gives the toughness, or it is also known as the strain hardening. So during the stress strain diagram, during the testing, what are the various mechanical properties can be applied to the stress strain diagram? Otherwise, various mechanical properties can be revealed during the tensile testing of any material. So those properties we will see now. So various zones, this gives a elasticity of a material according to the Hooke's law. And then a linear region. Linear region is at a proportional limit, point A. So stress is directly proportional to strain. There will be a linear relationship. But once the stress crosses, otherwise the stress strain diagram crosses a proportional limit, the non-linearity will take place. Stress is not directly proportional to a strain. Here this curve, and from this point onwards this becomes non-linear. So here from this point to this point, here you can see the ductility or deformation of the material. This is perfectly plastic yielding, and the strain hardening of the material will take place. Due to strain hardening, material will gets harder, and it requires more energy to break down. And at this point, necking will take place and fracture will take place. Strain hardening and necking. These are the various zones can be observed during the stress strain diagram. Here material is separated into two pieces, and here necking is forming at the ultimate, and the material will be as it is. Because once you remove the external load at the proportional limit, stress is directly proportional to strain. It will get back to its original state. Here we can see axis-centric load. This specimen is, if you keep into the universal testing machine, you can find out the linearity, non-linearity, where the Hooke's law can be applied, and where if a plastic zone is beginning, where the fracture is taking place, and you can find out a linear area. So here the Hooke's law can be applied, sigma directly proportional to strain, but here sigma is function of epsilon. So in this diagram we can see the various zones again, the plastic deformation and fracture, Hooke's law, where Hooke's law can be applied, and linearity, non-linearity, etc. So the definitions, various points on a stress strain diagram are proportional limit, elastic limit, yield point, ultimate stress point, and fracture or breaking point. These are the various points that we have located on the stress strain diagram. So now we will define the proportional. It is the region in the stress strain curve that obeys the Hooke's law. So in this limit, stress is directly proportional to strain, and material will get back to its original position. So within the elastic limit, so the non-linearity begins at after the proportional limit. The material will get back, but some of the residual strains will be remained. And the yield point, this yield point is nothing but where the plastic zone begins. So this is an indication of plastic zone of the material is beginning. And here we can see upper yield point and lower yield point. For some materials, upper and lower yield point will be there. For some material, we may not find out both the points, but yielding from yielding onwards, the plastic zone starts. It may be 1 or 2 points, and necking will be taking place at the ultimate stress. So now various mechanical properties can be obtained from a stress strain diagram are: the first one is stiffness. The stiffness means how a component is going to resist elastic deformation when a load is applied. So the elastic resistance of a material is known as stiffness. So from that, we can write stiffness is directly proportional to elasticity, and springiness is directly proportional to 1 by E. Okay, from Hooke's law, we can derive stress is directly proportional to strain, and we can replace proportionality with a constant E, and therefore Young's modulus is equals to stress by strain. So this is nothing but Hooke's law. So yeah, the slope indicates stiffness. To this, it indicates stiffness, and this is also elastic region, and the failure point will be here, and the non-elastic region, elastic region can be seen from this diagram, and this gives the elasticity of that material. Okay, non-elastic region and elastic region. Non-elastic region is nothing but the plastic zone of a material, and another mechanical property is strength. So how much of the this material it can absorb how much of the energy. So before fracture, it absorbs some energy. So that based on that, we can decide the material is having how much of strength, the capacity for high stress, ultimate stress. So because it has to resist the external deformation or external loading. So during this process, we can identify or we can measure. So what is the strength of that material? Next, yield stress. This is another mechanical property where at yielding the plastic zone will begins the lowest stress that produces permanent deformation. So permanent deformation, once the deformation begins, then it will not go back to its original position, or it can't obtain its elastic properties. And another one is oddness. Here we can find out oddness is a resistance to localized surface deformation. So oddness is nothing but resistance towards the external indentation or deformation, etc. So here we can associate oddness also with the stress strain diagram. And another one is toughness. The toughness is nothing but energy absorption of a stress strain curve. So this the area under the stress strain diagram is also known as toughness. Next, resilience. The resilience is nothing but deforming elastically. Elastic deformation is known as resilience. So this is another mechanical property. So can be understood from a stress strain diagram. Then ductility. Ductility is nothing but a deformation of a material when the external load is applied. So without breaking, it elongates to its maximum utility, maximum capacity. Then brittleness. So here brittleness also during stress strain diagram, if the material will going to fail here only without this all deformations, then we can say that material is brittle material. So it will fail without a deformation, without much deformation or without noticeable deformation, the material will break down. That is brittleness. This is another mechanical property which we can understand from a stress strain diagram. Now strain hardening. So strain hardening is increased yield stress or strengthening of a material by plastic deformation. During plastic deformation, the strengthening of a material, the strengthening mechanism of a material is known as strain hardening. So at point 1, here you can see at point 1, this is a proportional limit. Point 1 is proportional limit, point 2 is elastic limit. The difference between these 2 points at a proportional limit, if you release the external loading, the material will get back to its original position without any permanent strain or residual strains. But at point 2, if you unload it, then the material will not follow this initial path or the path through which it has come, but it will take a new path like this. So that the gap between these two lines is known as residual strain or permanent set. Now we can observe the stress strain diagram for different types of materials. So here we have gone through the stress strain diagram like this. This is for a structural steel alloy. So because a proportional limit will be there, elastic there, upper yielding, lower yielding, ultimate, and fracture point. These all points will be disclosed for a ductile material. So the example of ductile material is A36 standard structural steel alloy. Next, another one is the common general purpose aluminum alloy. Aluminum alloy, you can see the stress, how much of stress it can bear, and what is the deformation, what is the ultimate stress of aluminum if you compare with this steel material. Where the stress, ultimate stress is here, but for this ultimate stress is somewhere here. So this is the difference between these two, and we don't find the material curvature is different. Similarly, magnesium alloy, so it can register. Uh, if you compare with these two materials, it can bear the lower amount of loads, not much load, and but it gives a deformation more. So therefore, we can understand. But the here it is giving deformation, long deformation without failure. So therefore, it is a ductile material but not brittle material. Deformation is there, but it can bear a lower amount of loads only. But if you compare with the steel, it can bear higher amount of loads, and deformation is also high without breakage. And in this diagram, we can see type of materials, the curve A, curve B, curve C, and D. If you observe these four diagrams, the curve C gives, as we have discussed earlier, this is known as a ductile material. This is a ductile material, and point A, without noticeable deformation, failure will take place. Therefore, it is a brittle material. And this is like a magnesium. It extracts less amount of energy only. Okay, it can bear less amount of stress, but it gives a deformation like this, like a plastic. So the plastic material will be like this. So here it is not breaking down, but a little curve is there. Therefore, this material can be said as a stronger material. It is also comes under brittle material only, but a little deformation is there. Therefore, a little stronger. Here we can see differentiate between type of brittle material and ductile material. So in brittle material, deformation is this much only. So if you see the extension of ductile material, this is the amount of deformation we can see. So therefore, ductile material will deform, and it absorbs the more amount of energy. Not only deforming, it absorbs more amount of energy. Therefore, toughness is more. Here, very less toughness, and brittle material will give less deformation. And failure, if you observe these two specimens, the material is going to break down like this. These two are flat at the fracture zone, but here the curvature is going to be taking place like this. That is the difference between these two materials. Brittle will break down like that. Example is a glass. It will become into two. It is split off into two parts. But if you take a steel, the area of cross section will be gradually decreasing. At one point, it will break down, not suddenly. So this diagram also is providing various stress strain diagrams, various relationship between stress and strain for different materials. For pure aluminum annealed, the stress strain diagram will be like this. And molybdenum, aluminum alloy 7075T6, and mild steel stress strain diagram will be like this, as we have discussed now. And magnesium alloy will be so in this form. Here, one example is given to find out the proof stress like this. Once stress strain diagram is drawn, the offset yield stress or proof stress can be calculated at 0.2%, 0.1%, wherever you want. You can calculate from this diagram. So these are the strains. 0.2% means 0.002. Yes, here you have to locate one point, and you have to draw a line parallel to the existing line, because we need 0.2% offset yield stress for 6061 T6 aluminum. This is T6 aluminum. So this is a curve. So for this curve, we have to draw a line parallel to existing line like this. It will be intersecting at this point from this intersection, if you draw an horizontal line to intersect y-axis, it reads 310. So that is a yield stress or offset yield stress of 60626 aluminum alloy by using offset method. So at 0.2%, if you need at 0.5%, then you have to draw a line here. 0.3%, you have to draw a line parallel to existing line from 0.3. So then we will draw an horizontal line and we will identify the offset stress, offset yield stress. The Poisson's ratio is defined as ratio of change in width for unit width of a material to the change in its length for unit length as a result of strain. So this is nothing but a ratio of lateral strain to the linear strain. Poisson's ratio is denoted by mu or 1 by m. It's nothing but lateral strain to the linear strain. The relationship between these two. In general, the Poisson's ratio will be 0 to 0.5. The proof stress is nothing but the stress is just sufficient to produce and load a defined amount of permanent residual strain which a material can have without appreciable structural damage. So this arbitrary value will be different for different materials or different uses of same material. So like just now we have seen how do you find out the 0.2% or 0.3% the offset yield stress. So that is nothing but proof stress. Now factor of safety. The factor of safety is nothing but a ratio of ultimate strength to the working stress. So ultimate stress to the working stress, the material before going to apply or before going to be utilized in some application, it is to first of all its ultimate stress can be calculated. Ultimate stress of any material can be calculated. So after that, at what stress or at what will be the working general working stress for which it has to be a work. So that we will calculate. So based on this, we'll find out the factor of safety. What is the ultimate it will have during testing only we can find out this, and what is the working, where under which working stress level we'll utilize this. So similarly, yield strength by working stress that we can apply for ductile materials. So factor of safety should be greater than to 1 for any material, greater than to 1. If it is 1, the working stress is equal to ultimate, then the material will fail down. So it has to be greater than to 1, 2 times of working or 3 times of working, 4 times of working, so that the material will not fail at a lower amount of loads. A factor of safety of 1 implies no safety at all. So always 1 is not suggested. Hence, some engineers prefer to use a related term margin of safety to describe the design parameters. The relation between margin of safety and factor of safety is margin of safety is equals to factor of safety minus 1. An appropriate factor of safety is chosen based on several considerations. The prime considerations are accuracy of load and wear estimates, the consequences of failure, and the cost of over-engineering the component to achieve the factor of safety. For example, components whose failure could result in substantial financial loss, serious injury, use a safety factor of 4 or higher. So often 10. So non-critical components generally have a safety factor of 2. So based on the its requirements, its purpose, we have to choose based on seriousness of that material and purpose, critical its criticality. Based on that, the factor of safety can be chosen. An interesting exception is in the field of aerospace engineering, where safety factors are kept about 1.15 to 1.25 because the costs associated with the structural weight are so high. So in order to reduce the cost, the total cost involved, Therefore, factor of safety maintained at 1.15 to 1.25. This low safety factor is why aerospace parts and materials are subject to more stringent testing and quality control. Some of the factor of safety values for some devices: aircraft components 1.5 to 2.5, boilers 3.5 to 6, cast iron wheels 20, because cast iron is a brittle material, engine components 6 to 8, turbine components are 6 to 8, rotating and static. So wire wraps are 8 to 9. Principle of superposition. So the principle of superposition simply states that on a linear elastic structure, the combined effect of several loads acting simultaneously is equal to the algebraic sum of the effects of each load acting individually. So whenever a material is made up of different components, or if a material is a composite type of a material, and material different composed of different elements with different lengths and different areas. If you apply the total load on either ends, so we have to find out the deformation of individual component, and if you sum up the individual components deformation, then we will get the total deformation. So by applying the principle of superposition, we will divide each component. If a component is made up of 10 subcomponents, each is with a different length, with a different diameter, with a different properties. So in such cases, we find out the elongation or change in deformation or strain separately. Then we will, in order to find out the total strain, we'll sum up all these strains. So then we'll get a total strain or total deformation. So where with the help of principle of superposition, we can apply onto the component and we will find out the strain. So that is the use of principle of superposition. Here we can see the example. So a material is applied with a 25 kilonewtons here, 50 kilonewtons towards upward direction, and in the downward the 100 kilonewton. So there are three parts, 1, 2 and 3. So by separating, by given load conditions and lengths and properties, we have to separate into three sub components. So one component is split up into three components. The first component A, B. So this component can be drawn like this. So length of 1 meter, and the load here, since it is fixed, it is if you observe the 25 kilonewton on third component, so we will get 75 over here. The 25 towards down, but here under 50 kilonewton is there. Therefore, we will take only 25 kilonewton here. Another 25 kilonewton will be applied on the second component. Okay. So remaining 25 is compressive. Is going to be applied in the form of a compressive force on the second component. So we'll 100 kilonewton is towards down at the point B, but we will consider only 75 kilonewton, and remained is 75 kilonewton. That is a tensile, and another 75 kilonewton as it is fixed. We will take a load equal to this load, and the equal loads now you can see. Tensile 25 kilonewton, compressive 25 kilonewton, and again tensile 75 kilonewton. Here we will find out the deformation in each component: delta L1, delta L2, delta L3. What will be the total elongation of this component? So then delta L is equals to delta L1 plus delta L2 plus delta L3. So the delta L1 or L2 L3 equation is P1 L1 by A1 E1. Similarly, P2 L2 by A2 E2. Then P3 L3 by A3 E3. So this is the area of cross section. A is area of cross section, E is the Young's modulus, P is the load, and L is the length of a bar, length of the division, component 1. component 1, this implies the component 2 and component 3. So but here, since the second component is a compressive force, we will take negative delta L1 minus delta L2 plus delta L3. Similarly, P1 L1 by A1 E1 minus P2 L2 by A2 E2 plus P3 L3 by A3 E3. So there we will get the total deformation. Thank you. With this, I'll conclude the relationship between stress strain diagram and principle of superposition. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.